Welcome back from lunch, everyone. I hope the poster session was terrific and that you enjoyed a break. We have a great panel again this afternoon. We'll be hearing from two of our industry sponsors of IDSS, speaking, as Deborah Broad had said, about what keeps them up at night. Our first speaker is Alex Cosmas, who has actually managed to come and speak despite the fact that he needs to leave immediately for an international flight, so thank you very much for that. He is Chief Scientist of the Strategic Innovation Group of Booz Allen Hamilton.
Thank you. Okay. Can everybody hear me okay? I just got reassigned to Thomson Reuters. Okay, so I apologize for the cheeky title of, so you can predict the future, but can you change it? Really what it's meant to be is the talk that I'd like to give is about the implications for potentially machine learning causality. And I think it's obviously causality and causal inference broadly has been a topic that's been debated for decades about whether there's a there there. I think with the evolution, the recent evolution in data science, there is this obsession in my mind of applying machine learning to improve the prediction of sort of today's data sets and predicting something that is likely to happen using traditional classification models, and I'm not referring to of course, the academic community, but I'm referring heavily to the practitioners community. There is this desire for all of us to start to migrate to decision science from data science, and decisions aren't necessarily just driven by brute force binary predictions or PDFs. They're driven by understanding the whys, and so. All of you are familiar with the analytics hierarchy. There's nothing new here. We describe the system that we operate in. We describe, of course, and can predict likely outcomes. And then in a prescriptive world, we constrain our future and then optimize against it. The challenge is that none of our clients, no organizations, the Fortune 500, the large government agencies, tend not to make decisions off of these answers to these questions. There's a very narrow set of problems or class of problems that actually rely on answers to these questions, and that's because they live, in my opinion, in a correlation framework. So I'm still observing the past and, of course, extrapolating it forward. Whereas a causal framework for this same exact hierarchy would move me from what happened or what is happening to why is it happening. And historically, we've left the causal considerations, to use Judea Pearl's terms, to the mercy of intuition and good judgment. So the question becomes, can I describe or extract or infer from a large and growing data set the reasons behind a current state that I'm viewing, or a prediction of what is likely to occur? Or more importantly, can I simulate alternative futures that don't just optimize in the way a mathematical program and a linear program might, which of course includes a number of constraints and distributions, but can I actually simulate alternative futures where the output of one action results in a changed input to someone else's decision, which is generally the art of simulation. Agent-based models, discrete event simulations. This is how most organizations and most leaders make decisions. The majority of it comes from gut instinct experience, but there are increasing number of tools that could be used to actually support that or reject some of that intuition. And again, in the art of simulation, there still remains a problem today that we tend to focus a lot on. It's a modeler's world. So a modeler sits down at a console and actually programs in constraints, programs in the rules of a system. even in an agent-based simulation, for example. So in this era of big data, can we actually move towards getting better than expert judgment? Can we inform expert judgment? And that's one of the key questions that we at Booz Allen, and I think the consulting world broadly, is obsessed with, because our clients, frankly, aren't really interested in the correlation framework. So let me jump ahead here. So when we think about big data and what it means, you pick your favorite metric. It's being produced at record volumes. 80% of the world's data was created in the last 2 years, and that metric is expected to hold true in 2 more years. It's big. It's disparate. But the challenge, I think, in the data science community that we're all members of is that blind reliance on the mining of these data sets has actually led us, in many cases, to information overload and useless information overload. And I give an example of, we have data scientists that are thrilled about finding correlations like mosquitoes are attracted to people who just ate bananas, or animals that lay eggs don't have belly buttons. And these are great insights to find. And in the case of the latter, I think it's pretty obvious there's a good biological reason why animals that lay eggs don't have belly buttons. This one, we're not so sure. Does anyone know if this is true? Mosquitoes are attracted to people who just ate bananas? There could be a reason for it. But we're so often left with this binary correlation that the question becomes, now it's up to the scientific community. The data scientists are done, hand it off to the scientific community to tell us whether that's true or false, and why, and therefore can I then react and create a remedy to the problem. So I summarize all of this by saying the big data community is growing overly confident in data's ability to explain everything. There's a very frightening article that Chris Anderson, who was a former editor-in-chief of Wired magazine, wrote back in 2008, 10 years ago. And his statement and the point of the article was that petabytes allow us to say that correlation is enough. Science is dead. I don't need theory that is then that needs to be tested via experimentation, because I have basically quantified everything. And the more that I can quantify everything, the less I actually need theory. And I think that's frightening. If nothing else, as a scientist, I think that if data science is to earn its place in the science community, you obviously have to continue with the scientific method and actually leverage data to improve theory, not to replace it. So the question in my mind, and I introduced this and I mentioned Judea Pearl, I mentioned this in a Bayesian network paradigm, is can I represent that last problem we saw, which is mosquitoes being attracted to animals or to people that just ate bananas? Can I represent that in some form of a joint probability distribution? Can I represent it in a graphical model? And in a graphical model, I'm going to, in this case, have 2 simple nodes. A is banana consumption, B is mosquito attraction. And we use this as a very simple, fun-spirited, high-spirited example, but the same is true of cancer and smoking. The same is true of seatbelt usage and reducing fatality rates. So there are serious societal questions that are debated, and historically, randomized experiments have always been the gold standard for establishing causal effects. But in many problems, and I'd argue in most problems, a clean experiment is not feasible. The seatbelt example is a good case. I can't run a controlled experiment and force people to not wear seatbelts. There's a moral and ethical dilemma there. I can't have 2 different tax regimes affect 350 million Americans and test an outcome. I can't have 2 different carbon emission levels and check over the course of a century, check their impact on climate change. So because I lack the ability to run experiments in very important issues, I need to rely on observational inference and make, hopefully, the jump to causal inference. So in this case, where you see these 2 nodes, you'll have a joint probability distribution between the two. And all I can get out of that binary relationship is effectively correlation. Now, we as humans can clearly eliminate the likelihood of mosquito attraction causing banana consumption. We laugh at the idea that I was bit by a mosquito and now I crave a banana. But can the machine laugh that off the way that we can? And in a binary situation, it becomes difficult. I'd argue that the reason why Bayesian networks are so often called causal networks is because the more highly dimensional a problem becomes, the more likely I can eliminate causality through process of elimination and ultimately be left with the structure that does represent a causal framework. So what I mean by that is if we have 5 nodes in a network, there are multiple candidate structures that represent the joint probability distribution of those nodes. I can eliminate certain structures just based on sort of 2 or 3 main criteria. One, the easiest, is temporalization. A cause cannot go back in time. A cause cannot go back in time and create an effect. An effect has to occur after the cause. That sounds obvious, but in the world of quantifying everything, we are increasingly able to timestamp causes and timestamp effects in the sense that I no longer view smoking and cancer as a snapshot in time, but I can actually timestamp the behaviors that cause the effect. And you'd be surprised, the majority of candidate structures get eliminated by temporalization alone. The second is potentially maybe even simpler, which is mutual information, which is this idea that a cause has to inform an effect. I can eliminate candidate structures where I don't observe a mutual information or a correlation, but we don't mandate that it be linear. So we can eliminate the majority of candidate structures on the basis of those 2 criteria. And then the third is subtle, and this is the one I'll stop with, and that is this notion that that I can leverage spouses and children and ancestors of nodes in order to create rules, business rules around when causes and effects have to be, cannot and can exist. So the classic example is, rain and a wet lawn. So if anyone's sort of studied directed graphs, this is always the first example that's given. So if I have a wet lawn and I have rain, is it more likely that the rain caused the wet lawn or the wet lawn caused the rain? Obviously, we laugh that off just the same way. But again, the question now becomes, can I actually automate the learning of the directionality of the information flow? In this case, information flow obviously goes from rain to the lawn. How do I do that? Well, if I have 100 lawns in a neighborhood, I should observe if rain is a parent or cause of the 100 lawns being wet. I should observe perfect mutual information in the sense that there is no, if that is the true cause of lawns, if rain undoubtedly and exhaustively causes lawns to be wet, I have to observe 100% correlation between those 2 occurring. There can be lawns that, of course, are wet without rain via sprinklers or some secondary cause. But I can eliminate rain as a cause of lawns being wet if I observe 100% correlation. So similarly, if I observe, if I have multiple lawns that are wet without, of course, this idea of I'm going to observe certain lawns to be wet while other lawns are not wet, and I haven't observed the cause behind the wetness, i.e. the sprinklers being turned on and off, then I have to then agree to and accept that there is a latent cause that I can then, as a human, start to test for. So we are not in any stretch eliminating the human in the loop from determining which nodes, which data points I need to collect to test for correlation or test for causality. But just like in any machine learning problem, feature selection and feature engineering is the most important part of the process. It's not which method, which algorithm, which ensemble I'm going to use. The same is true here. I can't actually test for correlation if I don't have the causes and the effects already in my model to test. So I'll leave it in the interest of time, the ability to actually test and insert causality into this model requires a human in the loop to suggest that what happens when you consume bananas, you have three things that happen biologically. Body heat goes up, body scent changes, and your CO2 production level goes up. And are those then correlated to mosquito attraction? In a controlled experiment, all have proven to be true. So I can, by inserting, because I am a human and science is an important element of causality, I can insert this in part of my acyclic graph and determine then the directionality of causality. So at scale, the broader and larger these networks become, the greater we have the ability, the more constraints are imposed upon my network, the more spouses, the more children, the more ancestors I can actually test. And in the end, I can eliminate the majority of structures that are not causal and be left with the handful that could be. And then I insert a human in the loop in today's day and age to flag the correct one. So it's only a matter of time do we get to the point where I'm confident that with a highly dimensional problem, we should be able to conduct this experiment without a human in the loop. So I'll stop there. Thank you guys for the time. And I apologize, I need to run out in a few minutes. Is there one question? I don't know if we have time, but any? Okay, thank you.